Welcome back to this channel. My name is Dr. Arzu Jabra. I have a PhD in organic chemistry, and I am a organic chemistry tutor, and I'm also a academic mindset coach for college students. So, in this series of videos, we are going over uh, the Kaplan textbook for organic chemistry, and we're going over every chapter. I'll be solving every problem so you can actually follow through every problem with me. So there are two ways that this video series will actually be helpful to you, right? One is to actually just download the PDF from the link mentioned below, and then once you download the PDF, you can solve through it. And when you get an incorrect answer, you can double check the answer. You can go back to the explanation of that problem in my video. Or two, you can solve along with me and pause the video when we are solving the problems, right? And go ahead and grab the free PDF first and then solve along with me. And when I'm solving it, pause it, and then double check your explanation for every problem and make sure that you're using the correct logic to answer those questions. And so I'm also an academic mindset coach for college students. I help high achievers who are stressed and overwhelmed and are unable to take control of their time and their energy. I help them take better control of their time and energy, feel better, and feel more excited about college and taking competitive exams like MCAT. So if you have college blues or you are preparing for MCAT and have a lot on plate or not able to balance everything, however, you really want to get that awesome score at the same time, not feel burnt out in the whole process. If you need external help, feel free to reach out on the email linked down below. And let's get started with today's problems. So today we're actually working on alcohols and ethers. Let me share my screen here, and here we go. Okay. All right. First problem over here. It is really fast. I think somebody asked for the access to the PDF or like the Google Drive document, and it wasn't shared publicly, but now it is shared publicly. So you can feel free to totally um, download it there, and you're not required to ask for an access request through me. So it's like completely available publicly. All right, so first problem first. Alcohols have higher boiling points than their analogous ethers and hydrocarbons because. So the specific property of alcohols that is not shared by ethers and hydrocarbons is that they form hydrogen bonding. So option B is the correct answer. Tertiary alcohols are oxidized with difficulty because option A, there is no hydrogen attached to the carbon with the hydroxyl group. There is no hydrogen attached to the carbon bearing the hydroxyl group, and that actually is the correct answer because whenever oxidation is required, right, or in the process of oxidation, the hydrogen which is attached to the carbon, which bears a OH, has to be removed, right? It has to be removed to be able to form the double bond present on the carbon and the oxygen single bond. And that is why that's the problem. There is no hydrogen attached to the alpha carbon, so that would be the one carbon which is adjacent to carbon bearing the OH, so that is definitely a problem. So option A is actually like the correct answer here. Tertiary alcohol contains hydroxyl group with no polarization. That's not really true. They still have polarization. They're relatively inert. And that's why. Why are they relatively inert though, right? Because there's no hydrogen attached to the carbon with hydroxyl group. All right. Which of the following reagents should be used to convert an alcohol into an aldehyde, right? So we are going from an alcohol to an aldehyde, and we know that that is a one-step oxidation, right? So if you have an alcohol, so you can go from an alcohol to an aldehyde, right, to an aldehyde to a carboxylic acid, and carboxylic acid actually is a two-step oxidation, meaning in the first step, alcohol oxidizes to an aldehyde, and then in the second step, aldehyde oxidizes to carboxylic acid. So when we use a very, very strong oxidizing reagents like KMNO4, potassium dichromate, K2CR2O7, those reagents will actually give us two-step oxidation. They do not stop in the middle. They like directly give us the products of full oxidation. However, when we use weak oxidizing reagents like PCC, right? We have the Jones reagent here with H2SO4, right? So if we have PCC or PDC, those are weak oxidizing reagents, and when we have those, the reaction undergoes only one-step oxidation. So this is a one-step oxidation, will stop at an aldehyde, and that is why the correct answer for this problem is just PCC. Okay, all right, next problem. The reaction of 1 mole of diethyl ether with excess of hydrobromic acid results in the production of. Okay, so we have hydrobromic acid and we have diethyl ether. So this is the structure of diethyl ether with excess of hydrobromic acid. So meaning this, with the excess of HBr, right, will result in the production of what? So in the first step, right, of this reaction is that whenever we have an oxygen-based species in the presence of acid, right, that would always get protonated in the first step. So that would actually generate the protonated ether, right? And the second step of the reaction would just be the attack of Br minus. And so here we don't really have two choices, right? If the anion, which is Br minus, attacks from here or attacks from here, it doesn't really matter, right? They both are the same. So now the product of this reaction is going to be ethyl bromide plus an alcohol. CH3CH2OH. And so the correct answer is ethyl bromide, 1 mole of ethyl bromide and 1 mole of ethanol, right? Which is pretty simple actually. And we don't have methyl bromide because obviously we have two carbons on each side of this diethyl ether, right? So that is why we will get ethyl bromide and ethanol in the answer. So C is actually the correct answer. Okay, the next problem. Given the reaction shown below with metachloroperoxybenzoic acid, what is the stereochemistry of the product? So if you think about MCPBA, right? This is a good question. This is a really good question because they're testing you whether you actually understand or not that when you have MCPBA, right? Then in that case, we form epoxide on an alkene, right? And of course, well, this is the product here. I should just say MCPBA here. And now, of course, MCPBA cannot really dictate on what phase the epoxide is going to end up on the alkene, meaning that this epoxide over here can go from below the plane, right? But can also go from above the plane. Like MCPBA is just metachloroperbenzoic acid, meaning that metachloroperbenzoic acid cannot really dictate where this extra oxygen should end up at, whether this oxygen should be below the plane or above the plane, right? And to be able to do that, we actually do need very fancy reagents that can dictate whether the oxygen can end up below the plane or above the plane. And that's not in the scope of undergraduate organic chemistry. That's like the PhD level chemistry, right? So now, because both these possible products can be formed, meaning that we should be able to figure out the stereochemistry at both the carbon centers, right? So if the oxygen is going above the plane, then the hydrogen must be going below the plane, the hydrogen must be going below the plane. And so they want us to figure out whether the stereocenters are R or S, right? So if you think about this stereocenter over here, then we have oxygen 1, okay, highest priority, and then there's this carbon, which is number 2, okay, and then this is the carbon, which is number 3, and the hydrogen is the lowest priority. So we've got 1, 2, 3, and 4, okay. And then if we connect the dots, or like connect the arrow from 1 to 2 to 3, we are actually going anti-clockwise. So we're going 1 to 2 to 3. So we're going S, and hydrogen is below the plane. So the rule is, if the hydrogen is on the dash bond, right, or below the plane, in that case, and if you go anti-clockwise is S, and clockwise is R. And this is when hydrogen is on the dash bond, right? Or the least priority, number 4, is on the dash bond. However, when it's the opposite, if it's on the wedge bond, then the rules are the opposite. Then clockwise is S and anti-clockwise is actually R, right? And I'm pretty sure you know this already. If you're not, please go back and review your rules if I just like rushed through them really fast. Okay, so then we got that this is S, okay? And then if I think about the carbon on this side really fast, or then the first attachment is oxygen, number 1, this is number 2, this is number 3, and this is number 4. So we're going 1 to 2, 2 to 3 to 4. So then you've got an R configuration over on the other side, right? So this is an R. So meaning that I can potentially have an S and the other carbon center as an R, right? So I can say 2S, 3R. But if I was at this product, then I know that the stereochemistry would have been opposite. So I can also have 2R and 3S. So then these two answers are the possible stereochemistry of the product. So then 2 and 3 are actually both the possible products of this reaction. So option C is the correct answer. All right, what are the major products of the reaction shown below? And so if you think about it, this is also a really good problem. So now in the first option, right, in the first step, we know that we have a basic oxygen, and then, so this is like Williamson's ethers. No, this is like the opposite. This is reactions of ether with an acid, right? So we've got a ether. Now with the ether, you've got a reaction with an acid. So in the first step, you have a basic oxygen, and the basic oxygen is actually attacking or forming that bond with the hydrogen, because this is more like an acid-base reaction. So that would be the first step. And then in the second step, actually, the Br minus 1, 2, 3, right? 1, 2, 3, okay. The Br minus would actually attack. But where would the Br minus actually attack? So the Br minus would actually, so it has two options then, right? So it can attack over here. So then when that would happen, this whole species, which actually is a phenol, would be the leaving group. This would become the leaving group. So this looks like a really good SN2 reaction. Br minus, really strong nucleophile, will attack over here, right? And then this can actually become the leaving group. We do know that oxygen, which is protonated, for example, water, forms a really good leaving group, right? Because it doesn't have a negative charge on it when it is actually a leaving group. a little bit more explanation than required for this problem. But then again, the other possibility is that the BR minus could potentially attack here, right? A possibility, might not be a very real possibility. And when that attacks over there, this whole thing could have been a leaving group, right? However, that's a problem because this leaving group, when this whole species was acting like a leaving group, right, the negative charge would have attacked on a carbon, which is this one, which actually is an sp2 carbon, and a this is a leaving group, and a SN2 reaction does not actually happen at the sp2 carbon. So all the SN2 reactions that you have actually learned until now, those reactions only happen at the sp3 carbon centers. So SN2 reactions do not operate on sp2 carbon centers, and that is why attacking over here is definitely a problem. So the Br minus will go over here, and then this would have to be the leaving group. So the products that would be formed would be a phenol and 1, 2, 1, 2, 3, and the OH. Oh, I'm sorry, Br. So propyl bromide, right? 1, 2, 3. 1, 2, 3, propyl bromide would actually be the other side product of the reaction. So then the correct answer is we've got phenol. Okay, where is that? And bromopropane. Yeah, that's correct. Or bromyl. Or alkyl bromide or propyl bromide, right? So they both are the correct and naming for that compound. So option A is actually the correct answer for that problem. Which of the following compounds below can undergo oxidation reactions? We know exactly the first problem, right? For the oxidation to occur, we really need a carbon which bears the hydroxy. We need that carbon to have a hydrogen present on it, right? But the first compound over here does not have that, so it cannot undergo oxidation. In the second one, again, the carbon which bears a C double bond O, and for us to be able to further oxidize it, we need to have a hydrogen on that. Only then we can actually oxidize it further down to carboxylic acid. And so that's also not possible here. What about the third option? Now in the third option, we already have the fully oxidized product. So that's we cannot really further oxidize it to anything else. For the fourth option, we have an alcohol, right? And that alcohol also has a hydrogen over here. So that hydrogen can definitely undergo oxidation, right? So that's why then option D actually is the correct answer, because there's a possibility of oxidation because of that hydrogen present over there or there. So option D is the correct answer for that problem. Okay, what reagent most effectively produce the following transformation shown below? So for this problem, we do see that the OCH3, right, is actually the nucleophile, and that nucleophile ends up at a position at a carbon center amongst these two carbon centers, at a carbon center which is actually less substituted, right? Or the less hindered carbon amongst these two carbons of the epoxide. So we do see this side of the carbon chain and this side of the carbon chain. This side of the carbon chain is more hindered. However, this side of the carbon chain is actually less hindered. And so we've got a CH3OH, right? So we want a nucleophile which is negatively charged, because when the reaction of epoxide happens with the nucleophile which is negatively charged, right, then that nucleophile attacks at the less substituted carbon. But when we reacted with an acidic environment like H+, in that case, the reaction happens more like an SN1 reaction. So the nucleophile, which over here acts like a weak base, actually ends up on the more substituted carbon. So if you want the nucleophile to end up at the less substituted carbon, you really want to make sure that the nucleophile over here is going to attack at, or the nucleophile over here is in negatively charged, because that are the kind of nucleophiles, right, that are actually used in a SN2 type of reaction, and then the reaction happens at the less hindered carbon. So option D is the only option which actually has a negatively charged nucleophile. All right, really fast. I think I was thinking about one of the problem that we did earlier. And for that problem, if I review it really fast, right? Okay, not this one. The excess reaction. I think I did not consider one possibility in this reaction. And I was just thinking about that the reaction of 1 mole of diethyl ether with excess. So there is the one thing that you want to keep in mind when they're doing this category of reaction with excess of hydrobromic acid, right? So even after we have formed this product, it can still react with hydrobromic acid. And then, so we know that this hydroxide can actually become a really good leaving group because of the presence of acid. So it will first form OHH, so it will first form like water. And now we know that water is actually a really good leaving group. So now Br minus can attack over here to actually give us ethyl bromide again. So the correct answer for this problem is option A, actually 2 moles of ethyl bromide, and not C. So make sure that we're always reading every, or including every possibility in the problem. So because the reaction can happen again, it will just lead to the ethyl bromide. All right, so this was all for, these are all the problems from this chapter, and next time I will go over so now I think we're getting in the realm of Orgo 2. So we're going to do more of reactions and the reactions of different functional groups. And so if you have any questions about any of the explanation, or if you want me to explain anything deeper, feel free to leave me a message on, or an email on the links mentioned down below. And if you need my help, feel free to reach out. And until then, keep learning and keep growing. And I will see you guys next time. Bye now.